let's jump right into this explainer. Actually, let's go a step further. Imagine we're shrinking ourselves down to the size of a breadcrumb. Today, we're exploring the incredible, fascinating world inside your kitchen microwave. I want you to picture this almost like a beautifully animated, Studio Ghibli-style storybook journey. You know, a world where invisible forces dance around, giant metal walls trap bouncing energy, and tiny microscopic characters spin at literally lightning speeds. It's a real-life scientific wonderland, sitting right there on your kitchen counter. Now, think about this for a second. You open a cold metal box, you put in a completely cold bowl of soup, press a button, and just like magic, you get a piping hot meal a minute later. And the craziest part? There's not a single lick of flame. No glowing red coal, no hot stove burner. So how is that even possible? Well, it might feel like pure magic, but as we're about to see, it's actually some incredibly clever science. Chapter 1. The Melting Candy Oxidant. Our story actually begins way back in the military radar labs of the 1940s, featuring a brilliant inventor and, well, a very messy pocket. You know, some of the most amazing scientific discoveries come from total accidents, and this is definitely one of my absolute favorites. What's so incredible here is how a gooey, chocolatey mess led to a total revolution in cooking. So there was this self-taught American physicist named Percy Spencer. He was working on radar instruments during World War II, standing near a device called a magnetron. Suddenly, he realizes the peanut cluster candy bar in his pocket had completely melted. He's super intrigued, right? So he brings in some popcorn kernels, and boom, they pop. Then he tries an egg, which hilariously exploded all over a colleague. Fast forward to 1972, and this accidental, messy discovery had evolved into the very first commercial microwaves for our home kitchens. And this perfectly illustrates the fundamental difference between the old way of cooking and this brand new magic. See, conventional ovens heat your food really slowly from the outside in. It's kind of like waiting for a campfire to warm you up, you know? Your outer layer gets hot, but your core stays totally freezing. But microwave ovens, they use these invisible waves that penetrate a few centimeters deep inside the food right away. They wake up the molecules, make them dance, and generate heat instantly from the inside out. Chapter 2. The Heart of the Machine. To truly understand how this magic works, we need to meet the beating heart of our little metal box. Deep inside the walls of your microwave lives a magical little device called the cavity magnetron. You can think of it as like an electromagnetic whistle. Inside this vacuum tube, an electric field shoots out tiny electrons, and then these super powerful magnets push them into a curved, spiraling path. It's a lot like a steady, enchanted wind blowing a rolling marble into a smooth curve. The swirling, chaotic traffic jam of electrons sweeps past these little metallic cavities, blowing across them basically exactly like you'd blow across the top of a glass bottle, and that creates this high-energy, invisible song of microwaves. So the absolutely crucial thing to remember is this simple, four-step flow that happens every single time you press start. First, the magnetron whistle blows, creating the waves. Second, those waves shoot into the chamber and bounce wildly off the shiny metal walls. Third, the spirited little water molecules trapped inside your food hear this invisible song and just start to dance. And fourth, all that chaotic dancing creates friction, which makes your dinner hot. Simple, right? Chapter 3. Riding the Invisible Waves. Let's move right into the cooking chamber itself and see how this builds into an incredible bouncing ecosystem. Picture this chamber as a walled courtyard where invisible waves are just crashing back and forth. As they bounce off the metal walls, they cross over each other and create what scientists call standing waves. If you've ever held a jump rope tied to a wall and just shook it up and down like crazy, you know exactly what this looks like. You get this wave pattern where some parts of the rope are swinging wildly up and down, while other specific spots on the rope just stay completely, weirdly still. Inside our microwave, those wildly swinging parts of the jump rope are our hot spots. These are regions of incredibly high energy. But those parts of the rope that stay perfectly still, those are our cold spots with absolutely zero energy. And because a microwave is about 12 centimeters long, these really intense hot spots and freezing cold spots occur exactly 6 centimeters apart, forming this rigid, invisible grid all throughout your microwave. Now, this creates a bit of a problem. Think about it. If you took out the rotating glass plate, covered a flat dish with mini marshmallows, and just left it perfectly still in the microwave, what do you think would happen? Well, you'd end up with a very sad, very weird dessert. You'd see perfectly puffed, melted marshmallows exactly 6 centimeters apart, with completely cold, solid marshmallows sitting right in between them, stuck in those cold spots.
And that, my friends, is exactly why your microwave has a spinning glass turntable. It acts like a little magical carousel, slowly rotating your food. This ensures that every single bite of your meal gets a turn passing through those wildly swinging hot spots. It averages out the heat so your food cooks perfectly evenly. Genius, right? Chapter 4, The Water Molecule Dance. Now, let's zoom in really, really close. Shrink down so small that you can look at one tiny, individual water drop inside your food.
Water is what scientists call a polar molecule. Visually, it's actually shaped a bit like a cartoon Mickey Mouse head. Because of this totally lopsided shape, the oxygen face has a slightly negative charge, and the two hydrogen ears have a slightly positive charge. This means every single water molecule in your soup acts exactly like a tiny microscopic compass, reacting powerfully to electric fields. When that microwave turns on, it floods the chamber with an electric field that changes direction an astonishing 2.45 billion times every single second. I mean, 2.45 billion. Imagine this wild animated dance floor where the music tells the dancers to turn around billions of times a second. The tiny water compasses frantically flip back and forth trying to align with the changing field. As they spin, they violently bump and rub against all the neighboring fat, sugar, and protein molecules. And this intense microscopic friction is what actually creates the heat. You are essentially warming your food mechanically. Chapter 5, The Magic Metal Shield. As we finish up our micro journey, you might be wondering a bit about safety. I mean, how do we stay safe while standing right outside the door watching this wild, high-energy dance party taking place literally just inches away? Well, the secret lies in the door itself. Have you ever noticed that black mesh grid on the glass window? It's not just there for decoration or to tint the glass. It is a vital, highly engineered scientific shield. And the holes in that mesh are incredibly tiny, only about 1.5 millimeters wide. Remember how we said microwaves are about 12 centimeters or 120 millimeters long? It's like trying to throw a giant 120 millimeter beach ball through a tiny 1.5 millimeter hole. It's just not going to happen. The microwaves are way too gigantic, so they bounce right off the metal mesh and reflect straight back inside the oven. Visible light, on the other hand, has an unimaginably tiny wavelength. It slips right through those holes completely effortlessly, letting you safely watch your butter melt. Furthermore, microwaves are what we call non-ionizing radiation. Now, I know the word radiation sounds a bit scary, but in physics, it really just means energy moving across a gap. Unlike high-energy ionizing radiation, like X-rays, which are basically microscopic wrecking balls that can actually break DNA chains, microwaves are incredibly low energy. They only have enough power to make our little molecule friends jiggle and spin. They literally cannot alter atomic structures or make your food radioactive. Soup heated in a microwave is chemically identical to soup heated on a stove. But wait, if it's so safe, we've all heard the ultimate golden rule of the kitchen, right? Never, ever put metal in the microwave. So what is the actual science behind the dramatic sparks and explosions we've all been warned about? Well, metals are conductors, which means they are absolutely full of freely moving, loose electrons. Instead of absorbing the microwaves like a little water molecule does, the electrons in the metal just get pushed around by the waves. They run away and pile up at sharp corners, like the pointy prongs of a fork or the crinkled edges of aluminum foil. The voltage gets so incredibly high at those sharp points that it rips electrons right out of the surrounding air, creating a glowing, electrically charged gas called plasma. You are literally creating miniature lightning bolts right there in your kitchen. And yeah, you definitely want to avoid that. So the next time you pop your popcorn, I want you to remember this story. Remember the brilliant accident in the 1940s, the spinning carousel turntable, and the frantic billions of times a second dance of the tiny Mickey Mouse water molecules making it all happen. It really is an incredible, magical micro journey. Keep observing the everyday magic around you and, as always, stay curious.